So we have only 2 minutes left. Please, the first speaker, can you please share your PowerPoint right now? Bentao, I can't hear you actually. I think there's some internet issue.
Yeah, I will be.
Your voice is right. The first speaker, please share your PowerPoint right now.
I mean, according to the list, I think and Adazi was the first speaker. So, and I'm the second speaker. But should I go ahead?
Yes, yeah. Sorry, I was talking about you. Yeah, Samantha. Okay. Yeah, you're the second speaker, but the first speaker cannot doesn't work with his mic, so you will become the first one. Yeah, please, okay. please begin now. Sure, please. Thank you.
Okay.
All right. It's a very harsh moment because we have a lot of internet issue, but yeah. So we will have, for each talk, we will have about 15 minutes presentation plus 5 minute questionnaire. Samantha, now it's your turn to talk about the tidal heating on the brain. Please go ahead. Thank you.
Yeah, thank you very much, Kai, for your introduction, and thanks to the organizers for giving me this opportunity. And good morning, good afternoon, good evening, or good night, depending on which part of the world you are from. So today I will talk about tidal heating on the brain, in particular in presence of an extra dimension. And we'll discuss about implications for black holes and exotic compact objects. So this work has been done in collaboration with Shayok Datta, Shubhodip Shao, Romit De, Shukanto Bose, Kungsan Fukon, and Niesh Apshordi. So this is a brief outline of my talk. So I will talk about tidal heating for compact objects in the presence of extra dimension. Then I will talk about nature of these compact objects and how they affect the phenomena of tidal heating. And finally, some possible constraint on the extra dimension will be presented based on the phase of the gravitational waveform. So I've listed the 3 main references on which this talk would be based on. If you wish to explore this direction further, you can just note them down. So let us start by understanding what is meant by tidal heating. So tidal heating is a phenomena which is very common to any binary system, in particular the Earth-Moon system, and also in Jupiter and its satellites. So in particular, the volcanic activity in the satellite Io of Jupiter is effectively done, the reason being the tidal heating principle. So that's why tidal heating is a very well-known phenomena in planetary sciences. However, we'll not talk about planets in this talk. Rather, we'll discuss about black holes and as compact objects as black holes. So in particular, as 2 compact objects in spiral around each other, it turns out that due to the tidal effect, they generate gravitational perturbations, which is obvious. And these gravitational perturbations travel to infinity, and these lead to the well-known quadruple formula and energy loss from a binary system, and so on and so forth. However, a part of this perturbation also travels within the horizon or the surface of the compact object, and thereby changing the characteristic properties like the area, mass, angular momentum, and any additional hair those objects may incur. These modifications in the geometrical properties of compact object is what people refer as tidal heating in the context of gravitational waves. And this was sort of worked out in great detail by the paper of Alvi, which I have mentioned, and was resurrected in recent times by works from Poisson and Paolo Pani, Vitor Cardoso, and those groups. So effectively, this tidal heating is a very important phenomenon in the sense that the change of horizon area, mass, and angular momentum, we need to know them precisely if we want to track the evolution of the binary system. And these are further more important in the context of extreme mass ratio in spiral, where this tidal heating can play a very important role. Now comes the point that whether we have seen black holes or exotic compact objects. So before 2016 or so, people had thought that the observation of gravitational wave is actually from black holes. The reason being, if we think of normal matter field satisfying standard energy conditions, then there is something called the Bugdal limit, which actually limits the minimum radius that a compact object can have, a star-like object can have. And that is much, larger than 2m, macroscopically away from 2m. So therefore, one would have observed any such deviations. However, it turns out that there can be some exotic matter field which lead to the exotic compact objects, and they can actually mimic whatever we have seen from the GW and whatever arises out of black hole. Though there are subtle differences in the sense in the quasi-normal modes, for example, there are repeated appearance of these QNMs, which are known as the echoes. For the case of tidal love number, for black holes, they would have been 0. However, for exotic compact objects, they are non-zero, which is another signature. And even there would be effects in the tidal heating, as we will see. And but these exotic compact objects are often introduced using certain ad hoc boundary condition, I would say, because one just places a reflective membrane near the event horizon and says that, well, that is acting as a proxy for the exotic compact object. It turns out that such boundary condition, that is for black hole, we would have a purely ingoing mode, but for exotic compact object, depending on how its reflectivity comes from, which is still not a very clear question, such boundary conditions are more natural for black holes on the brane, as we will see, where the ingoing and outgoing of the reflectivity can be motivated from much natural origin. So this is the setup that we will work with. So effectively, we have a 5-dimensional space-time on which we have Einstein's equation holding true, but we want to find out the field equations on the 4-dimensional space-time, namely on the brane. So the effective 4D theory is what we are interested in, because we are observers in 4D and we do not have access to a high energy probe so that we can probe the higher dimension. So we are sort of contenting ourselves with the 4D physics. So how do we see the effect of the higher dimension? That appears through the modification of the gravitational field equations. In particular, the Einstein's equations, which is g mu nu equals to 8 pi gt mu nu in 5D, that when projected onto the 4D hypersurface gets modified. In particular, for vacuum space-time, we have this additional term, which is this EAB term over here. And this EAB comes from the existence of a Weil tensor in the bulk, while the 4GAB is the standard 4-dimensional Einstein tensor. It turns out that EAB is divergence-free, thanks to the Bianchi identity, and it is also traceless, thanks to the symmetries of the Weil tensor. So it effectively behaves as a Maxwell field with an overall negative sign. So that is why this is, we can sort of approximate it to be a Maxwell field, but with the charge sign being different. And as a consequence, one can derive static spherically symmetric solutions as well as rotating solutions. So we'll talk about the rotating solution, which takes the form which I have just written over here. As you can see, this is very much similar to that of a Kerr-Newman black hole, with an exciting difference that the sign is plus q square for Kerr-Newman, while in this context, it is a minus q. So if the sign term is negative, then that is a distinctive signature of the presence of extra dimension. And we'll see what happens to this negative term and how it affects the phenomenon of tidal heating. Now, when we want to get the tidal heating, we effectively have to solve for the gravitational perturbation, and they will satisfy a Teukolsky-like equation. So that would be separable into radial and angular parts, because effectively the energy scale that we are interested in will not affect the extra dimension that much. So the differential equation or the Einstein's equation will simplify quite a bit. And therefore, we will see that it is again a Teukolsky-like equation separating into radial and angular parts. But if you want to do it with most generality, then it would be a bit difficult. And there is absolutely no reason to believe that it should be a separable. And of course, one has to resort to numerical methods in those cases. Now we have a differential equation which one can solve under certain approximation, in the sense in the high frequency or in the low frequency limit, and maybe in the region which is close to the horizon, say, for example. And then we need to impose boundary conditions. So it's the boundary condition which actually dictates which type of solution to expect. And depending on the boundary condition, the solutions can change pretty drastically. So first of all, at large distance from the source, it turns out that the perturbation must coincide with the tidal field. So this result effectively comes from the membrane paradigm book by Kipthorne et al. However, one can also find it in this paper by Alvi, and some discussion is also present there. So effectively, this EAB are the tidal fields, and this is a particular combination of the tidal field, because this is what is related to the a certain Weil scalar in the Newman-Penrose formalism. So here M2 is the mass of the companion in the binary, B is the distance between the binary system, and 2y2m corresponds to the spin-weighted spherical harmonics, which appears naturally from the angular part of Teukolsky equation. And this y2m star corresponds to spherical harmonics, with theta naught and phi naught denoting the direction of the one of the binary companion in response to the other. And in the near horizon, of course, if we think that it's a black hole, then we have purely ingoing modes. While if we have an exotic compact object, then we have both ingoing as well as outgoing modes. So depending on which type of situations we are interested in, we'll either take purely ingoing solution or pure both ingoing and outgoing modes, leading to departures in the corresponding solution space. Now, what will be the next? So this was done by Hawking and Hartle long back, 1972. So they argued that if there is a gravitational perturbation, then that will modify the null generators, which is expected, because the null generators are for the stationary case, and the perturbations which are entering the horizon must affect the horizon structure, and thereby it will affect the null generators. In particular, the shear of the null generators is what it will modify. For the background spacetime, the shear would be identically zero. However, for the part-up case, there would be non-zero value of the shear. And it turns out that the rate of change of area due to the incoming gravitational perturbation. So there are gravitational perturbations which are flowing into the black hole. That is, of course, one part going towards infinity, but we are interested in the part which is going into the black hole. And that leads to a change of area. Here, T is the Boyer-Lindquist time coordinate, which is the time as measured by an asymptotic observer. And that is related to the integral of the shear in a certain tetrad system, again known as the Hartle-Hawking tetrad system, when integrated over all solid angles d omega. Now, using the Newman-Penrose equation, this sigma HH square can be related to psi 0, again the Newman-Penrose Weil scalar. So effectively, it's an integral of psi 0. And we know what is psi 0 because psi 0 satisfies the Teukolsky equation. And I have just mentioned about the necessary boundary condition. So therefore, by solving the Teukolsky equation under certain approximations, imposing these boundary conditions, we can get the corresponding expression for the sigma HH square. So it's effectively an integral over psi 0 d omega, and that particular expression is what I have written below over here. So as you can see, M1 corresponds to the mass of the object that we are interested in, or whose tidal heating we are considering. M2 is the second mass, which is causing this tidal effect. This chi1 corresponds to the dimensionless spin parameter, the ratio of A over M, and Q over M1 square is again a dimensionless parameter arising out of the extra dimension. And theta naught corresponds to the angle of the binary companion to which it is located on the sky. And capital A and capital B, as you can see, they are affected by this object Q over M1 square on these occasions. And this should be chi1 square. So this bar is sort of a typo over here. So it depends on both chi1, the dimensionless parameter, the masses, the charge, as well as on the impact parameter d, or the distance between them. Now we can also get the rate of change of mass and angular momentum. For that, one can refer to the first law of black hole mechanics, which relates the rate of change of area, or change of area to be precise, to the change of mass and change of angular momentum with appropriate coefficient. It turns out that the corresponding solution would be given by the one written here, where omega h1 corresponds to the angular velocity of the horizon, and I is a certain integral which one needs to determine. So for that, what one does is that one uses this particular equation dA by dt, and therefore one substitute it in this equation to get I theta naught, which is then substituted in the expression for dm1 dt and dj1 dt to compute the rate of change of mass and rate of change of angular momentum. So this is what we have plotted. So this plots the ratio of dj1 dt with that of its Newtonian value. And it turns out that this is equal to dm1 dt when the orbital and j are in the same direction. That is for the case of aligned spin. So as you can see, in absence of a tidal charge, which is q equal to 0, we have this black curve which ends over here, while in presence of the tidal charge, it ends over there. So there is a significant deviation in the rate when the tidal charge is present. Now, using the trajectory of the particle, it is possible to get the total change of angular momentum as the binary system starts from infinity and spirals down to a smaller distance. In that case, also, we observe that there is a significant change due to the presence of the tidal charge q. Now, finally, the constraint on the tidal charge. So we can take the ratio of the gr m dot and the m dot in presence of q. As you can see, there is a q factor over here, which is effectively the dimensionless combination. And this can be compared to that of the reflectivity. And using that, we can get a bound on q. So if we use the MREs, then from future observation from the mismatch in the gravitational wave waveform, we can actually constrain r squared to of order 10 to the minus 5. And r squared is related to alpha. So you can see if alpha is of order 10 to the minus 5, for a certain value of chi, this log q is of order 10 to the minus 6 or even smaller. So we can provide strong constraint on q from future observations. This is my final slide. So what happens for exotic compact objects? So for exotic compact objects, we can get an expansion as a power series in this epsilon, where Rs is the surface of this exotic compact object. And all the things, rate of change of mass, angular momentum, rate of change of area, they all get corrected by this particular relation. It turns out that the second order term, which depends on the reflectivity directly, it depends through log epsilon. And this is where the quantum nature of black hole can be very important, because epsilon, if it is of the order of Planck length, log epsilon can still be macroscopic. And it's a very similar phenomena that has been observed for the case of tidal love number as well, where there are corrections of order log epsilon to the theory. So whether it can provide any hint towards quantum nature is something that we wish to explore in the future. So I finish with the conclusions. So extra dimensions affect the tidal heating in a binary system in a significant manner, as we have seen through the plots, that there are significant departure. Then there are strong constraints on the extra dimension, which can be derived from future GW experiment like LISA, which can actually determine or work out the dynamics of the MREs. And finally, the rate of change of area for an exotic compact object may hide quantum signatures of black hole, because echoes are often considered as quantum corrected black hole. So those signatures can possibly be seen through the log epsilon term. So with that, I wish to thank all of you for your attention. And if you have any questions, please feel free to ask. Thank you very much.
Yeah, thank you so much for your talk.
Thanks.
So from the audience, anyone have some questions or comments?
I have one question. You mentioned you mentioned quantum mechanical signatures. You hinted toward an area, issues of area. Could it also, in some cases, involve something to do with angular momentum, or is it just primarily just an area calculation that give you quantum mechanical signatures to your problem?
Yeah, so this we have seen just the rate of change of area, but as I said, that rate of change of area can be related to mass and angular momentum through the first law of black hole mechanics, and therefore a similar dependence will also be there in both the mass rate of change of mass and angular momentum. So if we can observe this rate of change of mass and compute its deviation from what we expect from normal GR black hole, then that will also depend on the reflectivity through this log epsilon term. And that may also encode the signatures of any quantum nature of black hole. So yeah,
So the,
whatever I
so the
said,
reflectivity is the main thing that might give you quantum
Yes.
signatures.
Exactly. So for example, if you have Boltzmann reflectivity or some other reflectivity, because that has to come from the quantum nature. So those are all reflected into the second order term. And it holds that signature.
So anyone else have some comments?
Yes, maybe. Thank you for a great talk. And just from your formulas for the change of area, it seems that expansion of the horizon is vanishing. Is that the case? And if so, why? I don't really see that.
So you mean this sigma term, right? It comes from the shear.
Yes, and there is apparently no expansion term at least.
Yeah, there is no expansion term because that expansion term is what we have used to get this dA by dt. So the expansion is related to the rate of change of area density, if you think about it.
I see it now. Sorry. Yeah, I get it.
Yes.
Sorry.
Yeah.
Just wasn't clear on it.
Yes.
Thank you.
Thanks. Yeah, thank you.
Okay, thank you for your wonderful talk. Thank you so
Thanks.
much.
So I will stop sharing.
Yeah, sure. Thank you. So let's welcome our next speaker, Andrea Redazi, but actually he was the first, but there was some internet issue. So let's welcome Andrea Redazi. So please share your screen. Are you there? I think still there is some internet issue. Yeah, he's here. Oh, good.
Who is next speaker?
Next speaker is Andrea Redazi. So I think he's online, but maybe some internet issue from his side. Just wait for 1 minute, then we can go ahead.
Just tell. All right. Tell me when you want me to be speaker, and I'll do next after you tell me that.
Yeah, I think maybe there is some internet issue on his side. I think because I think so we can go to our yeah, I think we can go to our next stop.
And
yeah, and you can start. Yeah.
thank you very much.
Thank you so much.
I'm a little clumsy, so okay, I'm going to share the screen. All right.
Yeah, sure.
Okay. And I'm going to move this right in the middle, and I'm going to blow this up.
Yeah.
All right. Now, Gmail, rwill9955b@gmail.com. All right. Apologize for that. Now, I assume I have 20 minutes, correct?
Yep.
Thank you. Looking at the physics of what a quark star black hole binary would create in terms of gravitational physics, signals and new physics. Thank you. A quark star black hole parent, as would be gravitational wave generator, is brought up. Quark stars are anyway likely to be black holes above a certain mass length, where the quark star themselves obey thermodynamic laws, which in certain ways differ from the traditional black hole models. We list some of the probable consequences of such a binary, making predictions as to certain gravitational wave phenomena which will have an observational consequence, i.e. a gravitational wave, in quote, change of energy from a black hole quark star pair would likely be within 90% of the comparatively mass black hole binary pair. Now, let me get to the electromagnetic profile of the two cases would differ dramatically, and we conclude our inquiry with an open question if the generalized uncertainty principle could play a role in comparing the 7th and 8th equations of our presentation. Now, introduction. It is simple enough to visualize what happens. Can all of you read what I have on the screen? Hello?
Yeah,
right.
we can.
Yeah, we
Thank
can
you.
hear you. Just go ahead.
All right. All right. Thank you very much. It is simple enough to visualize what happens if a quark star and a black hole binary exists and what this would say about gravitational wave generation, which is open speculation, i.e., as the Weisman suggests, as a quark star binary pair. We also, at the end of this document, include what may be a linkage to what is known as GRBs and the formation of a quark star from a massive GRB formation explosion. The following from article as to the physics of quark star black hole binary pairs. Now, this is figure 1, and this is from reference 1. Quote, on the 14th of August, 2019, the LIGO-Virgo collaboration detected a gravitational wave signal believed to be associated with the merging of a binary stellar system composed of a black hole with a mass 23 times the mass of the sun and a compact object with a mass of about 2.6 times the mass of the sun. The nature of gravitational wave 190814 secondary stars enigmatic since according to the current astronomical observations, it could be the heaviest neutron star, the lightest black hole ever observed. And this is just some of what you would get in terms of the diagram. All right. Now, what is said, neutron stars and quark stars could coexist has been proposed and given in certain, in the detail of certain papers. End of quote. One of the models is proposed in 3, making a pitch for a sudden release of energy as the following mechanism. The total energy release in the neutron star conversion is different, but the total binding energy of the strange star is neutron star is strange star. The binding energy of the strange star and the total binding energy of the neutron star, BENS. In so many words, the template for examining what may be happening hinges upon a burst of energy, a difference of energy between a neutron star and a strange star being released. We see, though, that this does not have a lot to do with the observed change in gravitational energy, which is given in the following. Now, here then, which is that, what does this have to do with the quark star black hole binary? Look at Marguerite volume 1, as to what stage 1 has the change of energy. And you have delta E gravitational wave binaries. This is a traditional formula. The nub of this is that a binary system with a black hole and a quark star, the value of equation 1 would be enormous. Whereas we can do a further refine by writing a reduced mass. And then from 4, we have observing the binding energy with respect to a Schwarzschild metric. So it's a little bit different. In doing so, we have to consider what happens to the reduced mass if we have a transfer state for a neutron star to a quark star as one of the constituent components of reduced mass. Neutron star, the quark star transformation, and its energy release. The smallest, most massive, most compressed neutron star is about 17 kilometers in diameter. A quark star can be smaller than 11 kilometers in diameter. Having said that, now a transfer neutron star, what it entails. Quote, the possible distance of 2 families of compact stars, neutron stars, quark stars, leads to a scenario in which a conversion process between the 2 stellar objects occurs with a subsequent release of the order of 10 to the 53rd power ergs. End of quote. In so many words, we can have that we would have a 10 to the 53 power ergs is roughly 10 to the 55 giga electron volts, or 6.24 times 10 to the 55 GeV. This transfer of energy from a neutron star to a quark star would entail a gigantic pulse of energy, where the quark star would have about 10% less energy than a typical black hole equal mass. Quote, the dust cloud surrounding black holes becomes heated by gravitational forces, which emits extremely powerful radiation. A quark star is expected to emit radiation just 10% less powerful. So the final stop as far as the sign of GRB would be, in fact, signaling a transfer to a neutron star to a quark star, whereas reference 12 refers to accretion distance of a quark star is different from a black hole. From a black hole, note the following. In the Biermann battery mechanism for B field creation of a black hole, the mere act of electric charges and accretion distance of a black hole will create magnetic fields, and this has been understood since 1975. And we would see also too, by reference 12, and accretion distance about a quark star was also B field generation. However, strange stars exhibit a low luminosity but high temperature bremsstrahlung spectrum, which in combination with the emission properties of the accretion disk may be the key signatures that differentiate massive strange stars from the black hole. And here is the punchline on page 12. The characteristics of this disk spectra about black holes and quark stars also exhibit significant difference. Black holes, the maximum of the spectra, are located at higher frequencies and reach higher values than those for quark stars. In case of the static CFL quark stars with maximal total mass, both the spectral amplitude and the frequency at which the maximum is located have lower values than those for rotating cases with higher maximal masses. And this is our figure 2, which would be a quark star, where the curved black hole would be for a curved black hole. So in other words, which is that you get some very strange, this is a schematic of some of the diagrams you would get in terms of a curved black hole with a strange star and other things. And so the temperature profile of the thin accretion disk about rotating black holes and quark stars with the same total mass and spin parameter A. The static configuration is also presented. This is for electromagnetic generation of E&M signals for a quark star versus what we see for a straight up black hole. And they are very, very different. And this is what was the result of this type of signature right over in here. So then, which is figure 3, states there would be a close synchronization of time between a gravitational wave signal and gamma ray burst in an event likely connected to a quark star being formed. Likely, the gravitational wave signal between a black hole binary would obey equation 2 and be almost duplicated by a black hole quark star. But you would have that ERB signature initially, and then you also, as in figure 2 though, for 12, the difference will show up decisively in magnetic field behavior between the quark star and the black hole's electromagnetics, and the temperature mappings of the accretion disk would be very different. And here's a black hole. Here's a black hole crediting material from a companion star. The companion star would likely be a quark star with an accretion disk being siphoned off to feed the black hole, as shown in figure 4. And then, which is it, well, what does this say in effect? Which is it to do this, consider, which has then reference as to what is known as black hole mining. To do this, use from 15, the so-called black hole mining in a black hole atmosphere has to have a high temperature, low luminosity behavior of a quark star. And this is from a what is known as the blue shift argument. This is so-called mining from a star and a change of the energy. The precise language is that a quark star has a very specific temperature value and low luminosity. It's a very high temperature value and low luminosity, which could be attained via this luminosity. Whereas we have for equation 5 being low, the TH is much smaller than Planck temperature, whereas equation 4 would be comparatively enormous for a quark star due to the smallest of the picked alpha term. And I am referring to equations 3, 4, and 5. In this case, the alleged change in the mine energy would be enormous and related to a GRB signal for an evolution from a neutron star to a quark strange star. And due to the smallest of the picked alpha term, where to use the following term for gravitational release of energy from a quark star a black hole binary. And this is just a related formula. This should be compared with respect to derivation 16, which does not include relativistic effects, but is the result of slamming of a quark star with a black hole. Note that in the below is the magnitude of equation 7 and 8. Is the magnitude of equations 7 and 8 are the same. It'll lead to a question as to how to interpret the final period of rotation of a quark star with that of a black hole between merger of the two masses, which we call T twiggle to the 2/3 power 1, was the final period of rotation between the two masses prior to the ring down merger of the two to the 2/3 power. Conclusion. Figures 3, 4, and equations 6, 7, and 8 are needed to be numerically assimilated, but the real question is after the GRB blow-up would be an example as to an accreditation district would show to a quark star that the models indicate yes, but we do not know even now the precise nature of the electromagnetic signal to how long they would be lasting. As an example, in the Biermann battery model has been proposed to give a tentative magnetic field in tandem with gravitational wave releases. What is that B field detail is composed of the final period of rotation in equation 8? Well, this is equation 8. We don't know. That's an open question. We don't know. Finally, our final comment which needs to be investigated, which is the issue of Bose-Einstein condensation with the gravitons that they condensate for the formation of black holes. And does this play a role in a binary of a quark star black hole model? We think it does in a major way. Here's the idea that black holes as Bose-Einstein condensates of gravitons will naturally interact with respect to the physics of equation 4, equation 7, and equation 8. This is equation 8. This is equation 7. And this is equation 4. And this is what you might 3, 4, 7, and 8. And then, which is here is the condensation argument. And this itself is, this is M is an item, is a particle or something that is emitted from a black hole, NP. The number of gravitons. This is saying you have a black hole as a Bose-Einstein condensate. This is not my derivation. This is done in particular to a reference which I cite in the end of the paper. Here's the first term. The first term, M, is in the effective mass of a graviton. This is my take as to how this make it respect to commensurate to special relativity. M would be roughly about 10 to the minus 10 grams. So you get something like 10 to the 10 gravitons per primordial black hole that might be interacting, say, with a quark star. There's equation 9, equation 10, and equation 11 detail in our investigations of equation 4, equation 7, and equation 8. Okay, 9, 10, and 11. 9, 10, and 11. And let me see, 8, 7, and 4. And this is 3 and 4 and 7 and 8. All right. And well, where is this coming from? I said, yes, it does. So, which is here are the references. This is primarily the big one, which I was citing for the last set of equations. P.H. Chanabis, self-gravitating Bose-Einstein condensates of quantum aspects of black holes, was Heidegger Calmet, editor of Fundamental Theories of Physics, 178, Springer, Nature, Chan, Switzerland, 2012. With this, I'm sorry, is that I'm not a very polished lecturer. I'm opening the floor now to questions from the audience. And if I confuse you, I really apologize. So I ask questions from the audience. Hello, any questions?
Yeah, so any questions, guys? Thank you for your wonderful talk.
Well, I just am saying is that what I just am saying is also too, is that what I'm saying is that you, first of all, with respect to, you may have a situation where you have a blow up that would occur of one star that would go into another star, which was the massive release of energy, which was referred to earlier. And you still would have a binary. But still, though, in the process of doing this, you are still going to have to, you're still looking at this phenomena as a figure 4. You have what you might call a close synchronization of time between the gravitational wave signal and gamma ray burst, and an event likely connects to Quark Star being formed. And then you have the problem, though, which is that the gravitational wave signatures are similar, but which is you have something like a Quark Star being formed that is going to have very different electromagnetic signatures, especially if it's connected to, say, with a black hole, than just simply a black hole binary. A Quark Star black hole would perhaps have a different electromagnetic signature. The Biermann battery dynamics would be different. And the other thing is that the temperature profile that this is something to keep into consideration. The temperature profile, the thin accretion disk about rotating black holes and quark stars with the same total mass and spin parameter A. And well, they're not really the same. And this is from, let me show you where that 12 is a big one. And this is right over here. Alexandro Drago, Gisupi, Palriala, Irene, Parenti transition to quark matter and long gamma ray bursts. Right over here is quite a good read. And here's another one which says Cheng and Hago, can stellar mass black holes be quark stars? Well, similar, but you have differences. As I said before, you have differences in the electromagnetic spectrum. But still, though, which is to keep in mind that there'd be close synchronization between a gravitational wave signal and gamma wave bursts, and a connection for a quark star being formed. In other words, is that you have a number of effects which are showing up together. And this right over here, these two things right here are very important. Alexandro Drago, Gisupi, Palriaga, and Irene Parenti transitions to quark matter and long gamma ray bursts. This is an important article. And the next one to consider, is this is a very important article. Can stellar mass black holes be quark stars? Well, the evidence from what I'm seeing is that possibly, but you have an unstable situation. And what you have in a situation is that you might have an ERB type of burst, which is going to be occurring when you get something that would later be associated with a neutron star. And you have to consider this. So I want to ask you, do you have questions of what I am referring to? I apologize. I'm a very poor speaker.
No, you did an amazing talk. Don't worry. Yeah, it's really informative, actually.
Okay.
So I think there is no question from audience, I think.
Well, I have one very big one right here, which I want to share with you. The gravitational wave signal between a black hole binary with equation 2 would be almost duplicated by a black hole quark star. This is what you get. The gravitational wave signatures would be similar, but the magnetic profiles, which you're going to be getting, as referred to right over here, about the accretion disk, are going to look very, very different right over in here. This is what seems to be coming up. And the question is that, can you even do something like an accretion disk or Biermann battery? And the Biermann battery idea is just simply is that you would have some sort of ion charges or something like that, which would go in some sort of a rotating ring or something like that, which would be going about a either a black hole or a strange star. But here's the other thing, is that strange stars exhibit a low luminosity but high temperature Bremsstrahlung spectrum. Maybe the signal may be it's maybe a way of determining the difference between a strange star and a black hole. This may be what you have. Question?
Hello, can you hear me?
Yes, I'm very hearing impaired. It's not your fault.
Oh, sorry. I think this is time for us to move on a little bit due to the limited time because we have another meeting based on this Zoom account. And sorry for that, Andrew. We can.
You don't have to apologize for anything. You don't have to apologize for anything. I hope I didn't waste your time. I tried not to.
Okay, thanks. Could you stop sharing? Let's move to our next speaker, Xinjian.
Sorry, went out. Can you listen me? I'm Andrea Tarsi.
Oh yeah, Andrea, could you?
Oh, fantastic.
Yeah.
So can we move to my talk, please? Because I was the
Great.
first, and
Yeah.
later I have another meeting. Yeah.
Oh, I see. I see. Andrew, could you please stop sharing and?
Oh yeah, sure I will. I just don't know how to work this very well. I'm very clumsy. Let me just work at this. I'm very clumsy. I don't understand the system very well.
It doesn't matter. I can stop your.
You just disconnect me and then I'll reconnect.
No. I can make it your. I can stop your sharing.
I found you right here. So I apologize. I'll just mute myself.
It's all right. It's all right. Andrew, could you share your screen?
Oh, sure. As I said, I will stop. Sorry. So you want me to stop sharing it?
Yeah.
Okay. Thank you.
So yeah. So can you see it?
Yes. Yes. Great.
Okay.
Please take it away.
Okay. Yeah, fantastic. So first of all, I would like to say that I'm very uncomfortable with the online meeting, but you know, is the best we can do. I'm going to talk about recent work in collaboration with Salvatore Capozziello and Sergei Odintsov. Is about chaotic solutions and black hole shadow in FOR gravity. So in particular, the reference is this one, published this year in Physics Letters B. So let me go to the point. So the black hole horizon and the photosphere. So we know that one of the most fascinating aspects of black hole physics is that below a critical distance, also light gets trapped in circular orbits. In other words, no any signal can escape from the black hole gravitational attraction, at least at the classical level, below a certain radial threshold. So the photons orbit around the black hole. They design the black hole. They basically form what we call the Photon Sphere. Indeed, surrounded by a luminous photon ring. This is very important because it can be an important test of black hole horizon and does also general relativity. It appears, sorry, you hear me? Hello? Hello?
Yeah, we can hear you.
Yes, we can hear you.
Yeah.
Yep.
Yeah. Okay. So yeah. Okay. Yeah. Okay. So the photon sphere is basically a critical radius that is 3/3 of the Schwarzschild radius. It is designing a circular orbit.
Oh, Andrea, your screen has disappeared.
Yeah, I think we lost Andrea accidentally. Man.
One, do you think we just go to our next speaker? Maybe Renshin can manage in 12 minutes.
Okay.
Yeah.
Android is back. Yeah.
Yeah, thank you so much, Renshin. You just try to manage in 12 minutes, okay? Oh, he started sharing. Oh, no. Andrea, can you hear us? Oh my God.
Hello, Andrea. Can you hear us?
I've unmuted myself. Can you hear me?
And Andrea, yeah, we can hear you, Andrew. But I think we are trying to connect. We are trying to help with Andrea.
No problem. I apologize. I'm a terrible speaker.
No worries. Hello, Andrea. Andrea, can you hear us? I think we lost Andrea again. No.
Well, I hope I wasn't responsible for that.
No. That's the connection. That's connection issue.
Let me tell them we can proceed later.
Yeah. Let's move to Xinzhen. So Xinzhen, can you share your screen?
Okay. Can you see my screen?
Yeah.
Okay. So hello everyone, I'm Xinren, a PhD student at the University of Science and Technology of China. So first, I would like to thank the organizer of MJ16. It's my pleasure to attend this great meeting and introduce my recent work, data-driven reconstruction of the late-time cosmology, cosmic acceleration with FT gravity. So first, I would like to introduce this data-driven cosmic reconstruction, and then I will connect it with FT gravity. And then I will introduce the detail about this numerical reconstruction approach, and then give the summary. First, let's say our standard model of cosmology. In Lambda CDM model, we know that our universe is begin with the Big Bang and the inflation. After the radiation dominated stage and the matter dominated stage, now we are at the dark energy dominated stage. So there is many different observations through the Lambda CDM model, and also this standard model also developed with the time. We know that the accelerating expansion of our universe was discovered in 1998. So before that, we don't know that our universe is accelerating expansion. And after that, we know there is something we call dark energy in our universe. And then after this discovery, that we put the cosmic constant in our standard model. And this discovery also get this Nobel Prize. Although that the Lambda CDM model has get a lot of successful, but it also has some problem with today's observation. A very famous one is the Hubble tension problem. So we can see here is the different measurements of the Hubble constant. Yeah, so we can see this blue one is the direct measurement, and the red one is some observation in high redshift, and they get the Hubble constant depend on the lambda CDM model. We can say there is the tension between these two approaches. So there's someone would think that maybe the lambda CDM model is not the real model for our universe. Maybe there are some physics beyond our beyond the lambda CDM model. And besides the Hubble constant, the Hubble tension problem, there are also the cosmic constant problem, coincidence problem, and the tension between other observation data, such as the sigma 8 tension. So this problem in lambda CDM lead us to consider some physics beyond the standard model. So, but however, what the real universe looks like is known by the observation. So it's better to, from the observation, determine what our universe is, what our universe really look like. So there is a work by Professor Gongbo Zhang. He combined the different data set to reconstruct the equilibrium state WZ. This is equilibrium state of the dark energy. So here they use the lot of data, including the CMB data, supernova data, BL data, and so on. So they put this data in different redshift bin, and in each redshift bin, they determine a value of W by the MCMC method. And the W in high redshift bin is related to the low redshift bin by a pre-distribution. And after use this method, we can reconstruct this WZ. We can say in lambda CDM model, the WZ is a constant -1. Here it has the oscillating behavior. It's something like the dynamic dark energy model. But we also can look at if we use some scalar field or some special fluid as the dark energy. In the high redshift, there is, we can see this W is much smaller than -1. It will lead the negative energy density. So if we thought the dark energy is the scalar field or some special fluid, the negative energy density will lead some problem. So, but if we use this, we also have another way to explain the expansion of our universe is the modified gravity. In modified gravity, actually, it only exists the effective energy density. So if the effective rho smaller than 0, there is no problem actually. Yeah, so here we just focus on the FT modified gravity. This is based on the Tidal gravity. Here that the space-time that we use is Wesenberg space-time and the Wesenberg connection. In this geometry, there only exists the torsion and no curvature. So we can use this torsion as the gravity. And there also the physical parameter in Tidal gravity is this tetrad field. And we can, there has a relationship between this tetrad and field and this metric. So we can also use this relationship to get the connection between the Wesenberg connection and the Levi-Kivita connection. Then we can also find the relationship between the Ricci scalar in GR and the torsion scalar in Tidal gravity. Then we find the difference between these two scalar only difference by a boundary term. So this boundary term, we know it has no contribution to the physics in the action. Actually, the Tidal gravity is equivalent to GR. Similar to, we can extend the GR to FR gravity. We also can extend the typography to the FT gravity. Just write the torsion scalar as a function of torsion scalar in the action. And then we can, from this action, to get the field equation here. Also, if we just work in the cosmology, that we bring it in the FRW metric and get the modified Friedmann equation. Next, we also can rewrite this modified Friedmann equation by the effective energy density and the effective pressure. By this approach, that we can see here the effective energy density is the contribution by the additional gravity term, and it can replace the cosmic constant and be the reason of the accelerating expansion of our universe. So from this effective parameter, we also can get the effective equilibrium state for this FT. So what's more that here that we know that the T is a function of redshift, because the T is actually the -6 h squared here. And we also can write this FT function as a function of redshift. And by a approximate approach, that we can rewrite the Friedmann equation like this way. In here, we can see that we can get the f function at the redshift I+1 by the parameter at redshift zi. So if we get the evolution of h and h dot, then we can reconstruct this f by this relationship. So that now that we can begin with the data reconstruction W. So from the Friedmann equation, that if we bring the one W simple, that we can get the h, the evolution of h and h dot. And here that we use this first 29 bins of this reconstruction. And then that we can use this W to get the h and h dot. So one W can get one h and h dot evolution. And if we do it repeated this, and we can get the distribution of the h and h dot. Here that we can connect the h by the boundary condition. However, because the W actually is the different bin, in each bin, the W is the constant. This will lead, actually the W is not continuous as a function of Z. And this will also lead the discontinuous of the H dot. And this will also lead to some problem when we reconstruct the F function. To solve this problem, we need to use some other method. It's the Gaussian process. The Gaussian process can get a collection of the radium variables by some data point, and each radium variables is a Gaussian distribution. So also this variables is related by a convergence function and the hyperparameters, which can determine by the observation data. So here that we can use this GAPP, is Gaussian process in Python, to reconstruct the H and H dot. So in our work, we just use this Gaussian kernel. In this Gaussian kernel, we can see this sigma f and L is the hyperparameters. And if we get the evolution of H, we can get from the above. and then we can use that to determine the Hubble parameter, and then we can reconstruct the edge. So this is the the reconstructed result of edge and edge dot. So here we can see now the different with the overall picture. This edge dot is evolved very smooth. It's continuous. And then we can bring the edge and edge dot in this equation and to reconstruction this f. So here we get the f as a function of z. Here, this black one is the redshift. Is a reconstructed result by the mean of the edge and edge dot, and the blue one and the blue line and the yellow range is the mean 1 sigma 2 sigma of the reconstructed result. Also, we also wanted to this is our mean result, and we also wanted to find the analytical equation to describe this f function. So actually, we choose this sine function because there has oscillating behavior. So we will use the sine function to describe it. If we use this sine function, there is we need at least 3 parameters to describe the amplitude, the frequency, and the phase of this oscillating behavior. And actually, we find this model A, this function, and we use this MCMC method. We can get this the value of this parameter, and then we can show this is this black one is the best fit curvature, and this red one is the analytical function. So we can say it does fit very well, and this line is Lambda 3M model. And we can also find that the Lambda 3M model is in the 1 sigma range, inside the 1 sigma range. Also we can use the Friedman equation to solve use the modified Friedman equation to solve the W Z, the equal state from the function. We also use another model B. This model B, we only use 1 parameter. Also, this is a sine function. In this form, that it's very similar to the cosmology constant. And the model A is have the oscillating behavior, and also can describe our observation very well. Okay. So, so let's give the summary that we use a combination of the observational data to reconstruct the FT function, and this is we work it in a model independent method. First, we reconstruct the edge and the edge dot, and from the W, and then we find the edge dot is not continuous by directly use this modified Friedman equation. Then that we use the Gaussian process to get a continuous edge dot. Then we can reconstruct the F very well, and then that we found that the reconstruction result is consistent with standard Lambda CDM model within 1 sigma confidence level, and also this best fit value has the oscillating behavior. So we use this sine function to describe this oscillating, and we found our function can describe this oscillating behavior very well, and have a good agreement with this observation data. Okay, That's all for my talk. Thank you for your attention.
Great, thanks. We have time for one quick question. Okay, if no question,
I have one quick question.
Okay.
Yeah.
My very quick question is, sir, is that you've been using Gaussian type of approximations and, and a sinusoidal function. Is there anything to say in the dark energy spectrum that might allow for non-Gaussian type of procedures in terms of modeling or curve fitting?
Oh, you mean use different kernel function? Right?
Yes, the kernel function would be modified slightly. Do you have anything that would be something other than, or is that the only one that really fits all your observed data?
I think it's a different method for this Gaussian process. So actually, for our work, we only choose this Gaussian kernel. So it is the most useful one. Yeah, maybe it's. We didn't to find the difference if we use the different the kernel function, but we also found some paper that just work to find the difference between the different kernel function. We also reference.
That's what I'm aware of that. That's the reason I asked that question. Thank you, sir.
Thank you for your question.
Yeah, I think we have to move on. And Xing, please stop sharing. And Andrea, please try again.
Can you hear me now?
Yes.
Hello? Yeah. Okay, let me try to share the screen. So can you see the screen?
Much better, yes.
Okay, perfect.
Take it away.
So let me try to be quick. So the title of my talk is Chaotic Solution and Black Hole Shadowing in FOR Gravity. So indeed, we are gonna discussing the difference of a photosphere that is critical, is basically the sphere designed by photons, the critical sphere designed by photons around the black hole horizon. We want to basically use the photosphere as a probe of general relativity. Particular, we want to explore the difference of general relativity predictions and FOR gravity. And actually, we found in this paper, in collaboration with Capozziello and Odintsov, published this year, some surprising new news in the field. So the photon sphere is pretty appearing like this, as we know, and is at the critical radius around 3/2 the Schwarzschild radius, and typically at this radius there are exponential instabilities of the orbits, and as all the instabilities actually is a chaotic system. Therefore we can say there's a butterfly effect, and as we know, every chaotic effects are related to the controlled by a Lyapunov exponent. Actually, there is a conjecture of Maldacena, Schenker, and Stanford. They conjecture that the instability cannot grow more than exponentially, which is not a surprise. However, they make a strong statement that this critical value of the Lyapunov exponent controlling the exponential instability cannot exceed a critical value, which is directly proportional to the Bekenstein-Hawking temperature in black holes. Let me try to explain what they mean. Actually, to make a diagnosis of a chaotic effect around black holes, we can, for instance, consider a correlator or Poisson bracket in classical mechanics of azimuthal angles at different times, so out of time correlators, which can be described for chaotic systems by an exponential, and where lambda appearing here is the Lyapunov exponent. This can be generalized to a generic correlator or two operators, and you can average in a thermal system. And actually, oh, sorry. Yeah. So actually, the chaotic, the correlate, when the correlator start to explode is after a typical time, which is the scrambling time, which is inverse proportional to the Lyapunov exponent. So the Mandelsina-Schenker-Stanford bound or conjecture is that suppose you have any hand-body system, then this Lyapunov exponent must be lower than a certain critical lambda t that is proportional to the temperature of the system. And in particular for black holes, it should be the black hole temperature. So in general relativity and semi-classical quantum gravity, this conjecture seems to be solid, although it's not a precise theorem. And the Maldacena, Schenker, and Stanford, they claim that this can be extended in higher derivative gravity. Actually, we will see that this is not true. So parametrically, such a Lyapunov exponent is connected to the black hole horizon and thus also to the quasi-normal modes. So there is a connection, a very deep connection between the Lyapunov exponent, the circular orbits, and the quasi-normal modes characteristic frequency appearing in a notorious Regge-Wheeler equations. Thus also in gravitational waves, this can be important. So so this can be used to test standard theory of gravity, particularly if the Birkhoff theorem is valid, if there is any anomalous growing of the black hole horizon, because if so, then this is gonna affecting the photosphere physics. So we want to test such a conjecture. And the problem is that we have classical instabilities in F(r) gravity that are gonna having an impact in such a conjecture. So let's start with F(r) gravity. Notoriously, this is a action. It's an extension of Einstein-Hilbert action with an F. This is an equation of motion, which is pretty well known. This theory admits a Schwarzschild de Sitter solution. However, this doesn't mean, and this is a common misunderstanding in literature, this doesn't mean that this solution is stable in time. Indeed, even if F(r) gravity has spherical symmetric solution, this doesn't guarantee that they are stable in time. In general, this means that the Birkhoff theorem in general relativity is not valid for F(r) gravity. In particular, to show the stability of solution, one should consider the metric perturbation analysis. This is in general very technically challenging. However, in some particular solution, this is controllable. In particular, for the so-called Nariai black hole, which is a extremal Schwarzschild de Sitter solution. In this case, the metric can be rewritten as the following. For extremal, I mean that is the limit in which a Schwarzschild radius is saturating the de Sitter Hubble radius. So the equation of motion, they appear as the following. And then you can make a perturbation around the Nariai solution. And with so you want to make a metric perturbation and you obtain this equation for the metric perturbations. Finally, if you try to solve, you obtain a master equation controlling the metric stability, and you obtain that in a several regional parameters, you find instabilities. In particular, you see that this equation is almost for a large time, for large t, is almost a Klein-Gordon equation. Thus, the solution are stable if and only if alpha is between 0 and 1/2 or lower than 0, and alpha is controlled by F(r) gravity profile, the F profile. So this means that we have a new Lyapunov exponent different from general relativity that we dubbed the gravitational Lyapunov exponent. And there is a critical branch in which such a Lyapunov exponent can dominate over the standard orbital one. So this means that the Maldacena-Schenker-Stanford bound in this case may be violated if the effective mass of the scalaron in FOR gravity, if you want to call like this, but in this case is more parameter controlling the metric perturbation evolution. So if this mass is higher than black hole temperature. So can it happen in realistic FOR models? Yes. Actually, this is almost an ubiquitous phenomena in FOR models. For example, if you take polynomial FOR gravity, it's easy to show that this is going on for every theory with n higher than 2 and gamma n, the constant in front, higher than 0. The only theory that doesn't have this effect in polynomial FOR is Starobinsky gravity, where just the power is the power of 2, and is notoriously one of the best model for inflation. For exponential model of lambda CDM, actually we find again that there are instabilities, even if very with the characteristic time that is very slow. And even in Wu-Savitsky model, which is another notorious model, we still find instabilities. So the phenomenology for this is very interesting, because actually this is a prediction. The prediction is that the clear prediction is that the photon sphere has a secularly growing shift that eventually can be constrained and tested in next experiment and for next measure, like the Einstein telescope horizon, the next experiments eventually. And also, even in gravitational waves, we know that quasi-normal modes are connected to the Lyapunov exponent of orbits, which is not trivial, but is subtle, but not malicious. But still, this means that we can test the phenomena even in gravitational waves. In particular, when a black hole, under two black holes, they have a merging. Then after the ring down phase, you can try to catch effect, try to catch such an effect in the ring down phase. So indeed, you expect the Regge-Wheeler equations are modified, and in particular in approximation that the growing of the horizon is much smaller than characteristic frequencies, real and imaginary part of the frequency, we obtain a modified Regge-Wheeler equation with a characteristic frequency that is connected to the Lyapunov exponents, but is varying in time. And this is a peculiar prediction. Of course, the approximation here, once again, is that the time variation is small. But this is what we expect for this phenomena, because the mass, the parameters of the theory, they allow that are not already ruled out, they allow only for very very slow variation. But in our paper, we estimate that are possibly they can be tested if the mass, the effective mass of the scaleron is around 10 to minus 22 eV, but the effect can be visible only for a supermassive black hole of 10 to 6 solar mass or so. So let me go to the conclusion. So the conclusion is that in general, the Maldacena-Schenker-Stanford bound seems to be violated in FOR gravity, which is a huge news since this bound seems to be pretty strong in general relativity and sustained by holography. This physics actually is testable, in particular in black hole shadows physics from measures of the photosphere and the black hole shadow measurements, especially for supermassive black holes, and in testing the gravitational waves in the ring down, comparing the prediction of F over gravity with general relativity in a quasi-normal modes behavior. And there are several open issues. First of all, we know that quantum gravity may eventually provide higher derivative terms, so maybe this can have an impact on the analysis. And second, it's possible that in scenarios in which dark matter is composed by primordial black holes, perhaps the anomalous growing of primordial black holes can change the cosmological histories. So thank you for the attention, and that's all.
Thanks, Andrea. We have one quick question for Andrea.
Question. I have one very quick question. You mentioned the real and the imaginary components for the frequency. If you had cases, are there differences in the stability analysis as you had the real frequency, the real component of the frequency was much smaller than the imaginary, or vice versa? And would this in any way affect the, say, what you might call the physics of this equation right over here as an example?
Yeah, actually, this is a good question. In our case, as a first analysis, we consider the case in which the mass is much below both the frequencies.
The reason I asked it had to do with the question of your treatment of nearly extremal black holes. I said, which is I thought you do since comparison to real the imaginary components and their strength, that would enable you to get some more refinement of this right over here, perhaps get some sort of a bound to say the n.
Yeah, actually, the problem is that this analysis in full generality is pretty difficult technically. So this is analytical solutions are possible only in few cases, especially for nearly extremal black holes. The solution are analytical solutions. But I think in future it would be very interesting to make more involved analysis, eventually numerical analysis. This was the first work in this direction just of this year. But I agree with you that is not the end of the story somehow.
All right. Andrea, thanks for your talk again. And Andrew, thank you for your question. Could you stop sharing? And our next speaker will be Andrew.
And me again.
Yeah.
This time I hope I do a little better. Okay, hold on just one moment.
Yep.
Let me just do one thing right over here. I hope I do a little bit better. Okay. Let me get this right over here. This is the okay.
Can you?
Yes, I just blew it up. I blew this up right over here. Okay.
Can you manage to share your screen?
Yes, I will do that right now. Wait a minute. I'm just in. Let me just get. I'm trying to share it. It's just that. Wait a minute. I'm just being very, very stupid. I'm being very stupid about this. I apologize.
No worries.
And I'm trying to. Let me. How do I open this up? Because I want to share my screen.
Can you? Did you see the green button at the bottom of the Zoom window?
I see a green button at the top.
Share screen.
Oh, I see. I found it. Okay, share the screen.
Yeah.
Yes, I got it. Okay, and this is right over here. Yes, right over here. So I have it. Thank you very much. I hope this is a little bit better than the last one was a disaster. A solution of cosmological constant. using multiverse version of Penrose CCC cosmology and enhanced quantization comparative. All right. We bring up this study due to a general failure of field theory methods to obtain a working solution to cosmological constant problem. One of the reasons is that quiescence studies involving evolution of cosmological constant have failed to match up with early supernova data. And well, you can go ahead. We will first start off with the redone calculations of vacuum energy given in one and how we rescaled to be in sync with observed experimental values for vacuum energy. This is the traditional calculation, which is done right over here. This right over here is the overshoot. And this is just, this just simply isn't working. All right. Now, which is that, in saying this, we have to consider that the dark energy would be proportional to h over 2 pi to the fourth power, the dark energy to the fourth. So then the equation you have to consider is a wavelength of 10 to the 30th times Planck length, about 10 to 30th times a Planck bubble. Looking at now the modification of the CCC cosmology, we now outlined the generalization for Penrose CCC cosmology. And what I did was I looked at a partition function. The following is from 13 serious relevance to the final part of the conclusion that there are in universes undergoing Penrose infinite expansion contained in a mega universe structure. Moreover, each of the in universes black hole evaporation and with Hawking's radiation for decaying black holes. As each of the inner universe is defined by a partition function called this. This is a partition function. There's just an information, a symbol of mixed minimum information correlated about 10 to the 7 to 10 to the 8 bits per partition in the set before. So minimum information is conserved between a set of partition functions per universe. And this is before and afterwards. However, the non-uniqueness of information is put into individual partition functions. Also, Hawking's radiation is collated by a strange attractor collection of the mega universe structure to form the new inflationary regime for each of the n universes represented. Our idea is to use what's known as CCC cosmology, that is Penrose, is thought upon first have a Big Bang initial expansion for the universe, which is represented by that particular, this one of the, let's say you have n perhaps, universes, pick one of them, I. Verification's universe structure was represented. Compression, expansion information was stated. Non-uniqueness of information placed in each of the n universe fails ergodic mixing of initial values of each of the n universes, expanding from a singularity beginning. N S value, state value, and this is saying that entropy would be approximately equaling to, which you might call N, which is just simply bits of information. And so then what you would have is that the energy expression in energy expression would be that you would have what is known as a measure of E of I for the density of states for the partition function. So you would have a partition function for a universe. It would be roughly equivalent to this. It's a DEI, NE of I. Each of the E identified as equation R was the iterations for n universes, and this is for Penrose. So then what you would have was that you would have before the nucleation regime is that you would have a vacuum nucleation and to a fixed after nucleation regime. So in other words, you would have n number of contributions, 1 over n. And here's the summary of what you might call partition functions of the universe. You have vacuum nucleation transfer, and you go back to this iteration regime. For n number of universes, J1 being the partition function universe before the blend into the right-hand side. Let me, okay, this is, so what you get before the nucleation regime is that here you get, this is before the nucleation regime, is that this is before we have expansion of the universe is going to be equivalent to the number of partition functions connected with black holes in a particular universe that you would have. Was Damon claimed 1 and 2 is how they come up with a multi-dimensional representation of black hole physics and symbols, enable continual mixing of space-time. Now here's the modification of Penrose. We argue this modification is mandated by having the initial dark energy wave function set as 10 to the 30th L Planck. After setting this in place, we will be comparing this method to the Clatter argument, looking at Clatter quantization for a cosmological constant. And this is what I was doing. And what here is a standard action, which you get for relativity. This is just nothing very special in itself. And the idea was that here is the right-hand side is a general relativistic action. And this is what was done by Clatter. And our assumption is that phi is a constant, whereas we assume we use the approximation. We're using this particular approximation. This is an infinite square well in the bubble is space-time. Here's h of n right over here. And this itself would be in this particular regime of space-time. This would be the interior of a bubble of space-time, which is getting dumped, getting material dumped from the so-called ergodic mixing of other universes, goes into this right over here. This is equivalent, the right-hand side would be equivalent to, the right-hand side would be equivalent to, which I might call standard general relativity. So S2 is Clatter's idea of how to do this. S1 is the general relativistic. This is with respect to something like an infinite square well or spherical potential model of the interior, to say of a regime of space-time which is receiving mixing from the many universes. This right over here is our output, what you get right over here. And then what I was able to do was that here's 2 of n would be 0 in the interior. It would go to a very large value. This would be a way of bounding, to say, the cosmological constant. And you are assuming right over here a bounce 8 pi over 3 np rho minus rho squared of 2. This is the tension. All right. So what I came up with more was I said phi was equaling to a minus term and a plus term, and the C1 would be determined experimentally. And here, which is this term right over here, the negative term, this sort of thing is kind of like negative energy, which would be done from all the ergodic mixing, which would be put into the system. This itself would be the buildup proportional to a Hubble parameter, but with a bounce right over here. Here is the scalar potential that was used. And so what was the result? Well, since I don't have a lot of time, what I'm going to say in effect, which was with this right over here, this configuration was set in an interior spherical well. You would have a boundary regime right over in here, and you would have something eventually which would penetrate the spherical well. And when you would do this, is that you could just use a simple Schrodinger equation argument, which I have right over in here. And this is for the expansion away from it. And you could just simply just use, example, this sort of an argument right over here, just something very similar to standard quantum mechanics, nothing special in itself. But then, which is you come up with something that's somewhat interesting. And the thing is that you get a proportional value to say for a minimum time step, 1/2n plus 1 is a volume. Right over here, it's something equivalent to T Planck and other things. But this n right over here, this term coefficient of n, what you would be getting would you'd have to go back to what you might call this right over in here, this left and this right hand. This would be something like a spherical well or a spherical turn. And here's where it would come from the Claudic comparison. And then which is a B equals 0 in the interior of a well where you're getting stuff to say from all the other universes dumped in. And then what you would get afterwards, well, what you would get afterwards is that, first of all, you could get a bond for the n. N is a quantum number being proportional to T Planck. We have different restrictions to say what is it like the quantum states within the interior of that bounce state before you would have expansion to the regular universe. And here is the cloudy argument right over. I mean, this is Kuiper wave functional. This is a somewhat similar to a dust model. And this, after you'd had the interior, the input and output, you could come up, they say, with some addition. Okay, so one of the things that you could do would be to say you had phi. Here is from the square, I mean, from a spherical well or something like, here's the C1. And you'd want to compare this with this sort of behavior right over in here, which is phi. Here's the interior of the well. Here's, a set. And here's something you get with respect to boundary conditions. So you would want to have that this is going to be equivalent. You would pick a C1 so that these two things would be giving equivalent information. And
can you hear me?
Yes, I'm nearly done.
Yeah, I'm sorry because we have to manage this Zoom.
Yeah, I'm going to go straight over to the main point.
Thank you so much.
Well, why don't we just say, if you want me to stop right here, I can, because I got to the main point.
Yeah, you just, okay.
The main point had to do with this right over here, this right over here. This, my main point is here is you have something right over here where this is solved at the interior of a regime of space-time regime set from the mixed universe contributions. This is solved is you have a plus and a minus term. You would have this, what you might call the setting of a dark energy wave functional, which you would have to work with. You can get these things equivalent and set up like this. This is the main point of my talk. All right. And there's not much more I really can say because I wasted your time with the other talk, okay, and which I'm apologizing for. But this right here is my main point of my analysis. So all this right over here is respect to a cosmological bounce. This is receiving information to say from the prior universes, like a mega universe structure in 1 over n times the mega universe structure was things put into there. This on the right-hand side with respect to boundary conditions you'd get. You'd want to set the C1 in a situation so that this would be equivalent to satisfy what you might call to have some consideration with respect to the, something proportional to, at least in fidelity, with respect to this right over in here. So that's what I was trying to do. Now, which is, since I wasted your time so badly before with the other talk, I just am saying is that here's the constraint upon 8 pi 2n plus 1 less than or equaling to 1. This is one of the weird things that seem to show up. All right, that was a minimum condition to say for like n, and this would be quantization within the bound that would be dumped in from the components of the mega structured universe. Now, which is that I'm opening the floor for questions.
So anyone have some questions, please?
I'm very hearing impaired, so someone's gonna have to speak up.
I think there is no more time for the question. So is it okay if you are going to stop your share and we are going to move for the next speaker?
Thank you. I hope I didn't waste your time in this one.
No, thank you. Is it fine if you just share your
Okay, let me just, I have to prepare for something else, but I want to say thank you very much for your great session. Thank you. And I'm going to mute myself.
I think it's my turn.
Shami. Yeah, yeah.
Okay,
Thank you.
thank you. Okay, can everyone see my screen?
Yeah, you just
Okay.
go ahead.
Okay, thanks. Hello, everyone. I am Shammi Tahura. I'm from University of Virginia, and I'm going to talk about gravitational memory waveforms in Brand-Sticky theory. Okay, so what are gravitational wave memory effects? Gravitational wave memory effects are associated with permanent change in the space-time due to propagating GWs. And the most familiar memory effect is the displacement memory effect, which says that before and after a burst of GWs pass by distant observers, the separations among the observers, they'll have a permanent shift. So these effects are closely related to the symmetries of asymptotically flat spacetimes, and they are well studied in GR, but not in modified theories of gravity. So in our work, we pick Brand-Sticky theory, which is one of the simplest modified theories of gravity. And this theory is relevant in the context of inflation and the accelerated expansion of the universe. So in our work, what we compute is the Newtonian order nonlinear displacement and spin memory waveforms, which also contains the leading order Brand-Sticky corrections. And we work under the assumption that Brand-Sticky corrections to the waveforms are subdominant compared to their GR counterparts. Okay. So in Brand-Sticky theory, we have three polarizations, two tensor modes, the plus and cross modes, which are also present in GR, and we have one scalar or breathing polarizations. And in our work, we will focus memory effects in the tensor polarizations. In these pictures here, I schematically show memory effect in the plus polarization. So if we have a ring of particle, and if gravitational waves and scalar waves are propagating into the page, then this ring of particle, it will stretch vertically, go back to circular shape, stretch horizontally, and it will keep oscillating this way. And once the wave is gone, if there is no memory effect, the ring of particles, it will be left in the circular shape, the original shape. But if there is a memory effect, this ring of particle, it will be left in a deformed shape. Okay. So to study memory effects, we consider first Brand-Sticky theory in Bondi-Sachs framework. So here is the Brand-Sticky action in Jordan frame. In this theory, we have a massless scalar field lambda, which is non-minimally coupled to the Ricci scalar. And this omega here is the Brand-Sticky coupling parameter. So varying this action, we find the modified Einstein equations. This G mu is the Einstein tensor. We consider vacuum, so on the right-hand side, we have only terms that involve lambda. This is the stress energy tensor of the scalar field. And we also have this field equation for the scalar field. This box is the D'Alembert of this metric G. And we consider an asymptotically flat metric in Bondi-Sachs form, which is written here. So we express this metric in the coordinates retarded time u, areal coordinate r, and x uppercase A, these denote the two angular coordinates. And this metric is subjected to Bondi gauge and it's parameterized by 4 functions of coordinates. This HAB is called the conformal 2 metric. We expand this conformal 2 metric in inverse of the radial coordinate. The leading order piece is the round 2 sphere metric. The coefficient of 1/r It's called the shear tensor, and it's related to gravitational waves. And there are higher order terms that I do not show. Similarly, we expand the scalar field. The leading order piece is a constant, and lambda 1 here is the leading order dynamical piece. And there are higher order terms. And we plug in this expansion in field equations, and we solve for the metric functions at various orders of 1 over r, and also we solve for their evolutions, and together they constitute the asymptotically flat solutions of Brans-Dicke theory in Bondi-Sachs framework. Next, we compute the asymptotic symmetries of asymptotically flat spacetime in Brans-Dicke theory, and we find that this is same as the symmetry group of GR, which is the extended BMS group. So if C is the generator of symmetry, then at null infinity, this C is expressed here. This alpha here is called the super translation. It forms an infinite dimensional group of translations, and these translations can be thought of angle-dependent translations. And Y here is the generator of Lorentz group, but it can also be promoted to an infinite dimensional group of super rotations or super boosts. And this H here is the covariant derivative compatible with the round two sphere metric. Super translation symmetries, they are associated with displacement memory effects, and super rotations or super boosts, they're related to spin and center of mass memory effects. Okay, so there are fluxes of conserved charges associated with the asymptotic symmetries, and we computed those following the modified Hamiltonian approach given by Wald and Zupas. And those fluxes of conserved charges, they give us some balance laws, which allow us to compute the memory effect in the gravitational waveform string. So this is what we find. Displacement memory, it enters in the plus polarization. It is sourced by the energy flux radiated into tensor fields or tensor gravitational waves, plus energy flux radiated into the scalar waves. And spin memory, it actually enters in the time integral of the cross polarization, and it's sourced by the angular momentum flux radiated into the fields, both tensor and scalar. In case of GR, we won't have this scalar here and here. If we consider vacuum, we just have the tensor fluxes. Okay, so now if we say want to compute the memory effect in the waveform, for example, generated by a compact binary, then we need to evaluate these right-hand sides. So on the right-hand side, these tensor fluxes, they're a function of the shear tensor, and the scalar flux is a function of lambda 1, the leading order dynamical piece of the scalar field. So if we want to evaluate these right-hand sides, we need expressions of shear and the scalar field generated by compact binaries. And to have those expressions, we look at Brans-Dicke theory in harmonic gauge in post-Newtonian framework. In post-Newtonian framework, we do similar expansion of the scalar field in terms of the harmonic gauge radius, and we expand the metric in terms of flat metric and this tensor H tilde and also the scalar field. And this metric is subjected to harmonic gauge, means that this H tilde mu nu is divergenceless. And the transverse traceless component of H tilde, we can expand it in terms of radiative mass and current multiple moments. This T, E, and TB, these are second rank tensor spherical harmonics. Okay, so now what we want to do is this H tilde is a TT. We want to relate it to the relevant quantity in Bondi gauge, which is the shear tensor. Similarly, this scalar field in the harmonic gauge, we want to relate it to the similar quantity in Bondi gauge. To do that, we perform coordinate transformation from harmonic gauge to Bondi gauge. And from that, we find that the shear tensor, it can be expanded in terms of the same radiative mass and current multiple moments of the harmonic gauge this way. And So then this U and V for quasi-circular binary, for example, we can find them in the living review of Blanchet for GR. And for the leading order piece, the U22 piece, we can compute it from Lang 2014. Similarly, for the scalar field, we find that this lambda 1 in the harmonic gauge is the same lambda 1 in the Bondi gauge, and we can use the solution of lambda 1 for a quasi-circular binary found by Lang in 2014. So then what we do, we use these expressions in our balance law, and that gives us the gravitational memory waveforms. Okay, so first I am showing the displacement memory waveform. So let us consider a binary of masses M1 and M2, sensitivities S1 and S2. Sensitivities are like scalar charges. Omega is the orbital angular frequency, and iota is the inclination angle, which is the angle between the direction of total angular momentum and also the line of sight. M is the total mass, eta is the symmetric mass ratio. And this X is the post-Newtonian expansion parameter. And a delta X means we are considering the change in X between some final time U final and initial time U initial. Capital S is the difference in sensitivities of the two components. And this C here, it's like the inverse of the Brand-Sticky parameter. It's a very small parameter. And we work under the assumption that C is much, much smaller than X, which ensures that the Brand-Sticky corrections are smaller compared to the GR contributions. Okay, so here are the waveforms, displacement memory waveforms. I am separately showing the contribution of the tensor energy flux and the scalar energy flux. And this first term here is the zero-PN GR memory. The terms in green, blue, they show the leading order Brand-Sticky correction, which enters at -1 p.m. And we also computed the Newtonian order Brand-Sticky terms, which are linear in C, sourced by both scalar energy flux and tensor energy flux, but the expressions are long, so I don't show them here. But these terms have an important feature, which is that they depend on the inclination angle differently than the zero-PN GR memory. Okay. Okay, and this term here, the leading order -1 PN memory sourced by the scalar energy flux, it matches with a similar term found by Lang in 2014. So Ryan Lang computed the tensor gravitational waveform generated by compact binaries by in the method of direct integration of relaxed Einstein equation. And at 1.5 PN order, there was a memory term. And after integrating over binaries history, which is similar to this -1 PN term that we found by scalar energy flux contribution. But our result is complete to the Newtonian order, which was not present in this work. Okay, so next I'm showing the spin memory waveform. Spin memory waveform has the same kind of feature as the displacement memory here. I'm showing the total contribution here, both scalar angular momentum flux and angular momentum flux of the tensor fields. So this is the zero-PN GR memory, which goes like x to the power -12. The leading order Brand-Sticky correction is at -1 PN. This term has same dependence on the inclination angle as the zero-PN GR memory. But zero-PN GR memory, zero-PN Brand-Sticky correction, similar to the displacement memory case, it has a different dependence on the inclination angle. And both in this case and the displacement memory case, the main reason of this different dependence on the inclination angle is that we need higher order radiative mass and current multiple moments in Brand-Sticky theory to compute zero-PN memory compared to that of GR. Okay. So to summarize, symmetries of asymptotically flat spacetime in Brand-Sticky theory is same as the extended BMS group. And from the fluxes of conserved charges associated with the symmetries, we computed tensor displacement and spin memories. And we found that these memories receive contribution from higher order radiative multiple moments. And because of that, they have a different dependence on the inclination angle compared to their GR counterpart. So thank you. That's all from me. If anyone has any question, I can take it.
Thank you so much for your talk. So any question from the audience?
I have a question.
Mhm.
You have considered a constraint xi much less than x. What is the motivation for this constraint?
Well, so the Brand-Sticky parameter, actually, it has already been constrained to be, this C has constrained to be very small from solar system experiments. So, and also like, it makes sense to consider the case where GR is dominant, since solar system and other kind of experiments also showed that the Brand-Sticky contribution to those cases are subdominant. So that's the motivation, actually. That's why we also considered here C to be much, much smaller than X.
Okay, thank you.
Okay, thank you so much, Shami. Thank you for the wonderful talk.
Okay, then if no one has questions, I'll stop sharing.
Let's welcome our Akira, right?
Hello, am I audible?
Yeah, now we can hear you.
Okay.
Harkirat Singh Sakota, right?
Yes, thank you. Okay, hello everyone. I would like to start by thanking the organizers for giving me this opportunity. The title of my talk is Operator Ordering Ambiguity in Observables of Quantum Cosmology. This talk is based on some preliminary results from work with my supervisor, Dr. Kinjal Klochan. Here in this talk, I will introduce the operator ordering ambiguity in the quantum cosmology model and discuss its imprint on the observables of quantum cosmology. I will start with canonical analysis of FRW model, with briefly discussing Brown-Kukash prescription for dust degrees of freedom. After that, I will write the quantum model for FRW model with Brown-Kukash dust, and after that I will write the canonical expressions for Hubble parameter, Ricci scalar, and Krushman scalar, and discuss their behavior in this quantum model. Now the FRW model is maximally symmetric spacetime with line element given in equation number 1. So the central object of interest is the scale factor from which the properties of spacetimes can be determined. The script n is lapse function, and small k is the spatial curvature. The Einstein-Hilbert action for this model is given in equation number 2, and the canonical momenta conjugate to lapse function vanishes in this model, which is the primary constraint of the theory. And the canonical momenta conjugate to scale factor is given in equation number 3. The Hamiltonian constraint for flat FRW model, that means when spatial curvature is 0, is given in equation number 4. For the case when with FRW model with dust as matter source, the solution of Friedmann's equation is given in equation number 5. Scale factor in this case is proportional to tau to the power 2 by 3, and Hubble, Ricci, and Krushman scalar for the model are inversely proportional to tau. At tau is equal to 0, scale factor vanishes and the curvature invariants diverge, and thus this represents a singular configuration. Next, we will introduce the matter degrees of freedom and intend to use it as clock variable in the theory. For that, we use Brown-Kukash model of dust, which is a well-known prescription to deal with the issue of time. The action for dust is parameterized by 4-vector u mu and scalar function rho. The scalar vector decomposition is done for the 4-vector into a scalar function capital T and 3-vector capital W and capital S. The equation of motion for rho ensures the normalizability of the 4 vector, and the stress energy tensor computed from the action given in equation number 6 takes the form for the dust with rho its energy density, and the scalar function capital T will be taken as time variable in this model. When we do 3+1 decomposition of this Brown-Kukash action, the contribution to Hamiltonian constraint and momentum constraint takes this form. For symmetry reduced models such as FRW model, we can choose three vector capital W and capital S to be 0, and the scalar function depends only on time. And this function will play the role of time, and the Hamiltonian constraint in this model then takes the linearized form. Now with this Brown-Kukash test, the Hamiltonian constraint is given in equation number 7. We will take the quantum model constructed by Kiefer and Schmidt, which is given in this reference. Now, since the Hamiltonian constraint contains a term which is product of scale factor and its conjugate momentum, therefore it will exhibit operator ordering ambiguity, which means that this classical expression doesn't have a unique quantum counterpart. The Wheeler-DeWitt equation for this model is written in equation number 8, which takes a Schrodinger-like form. The parameters small p and small q encapsulate the operator ordering ambiguity. This Hamiltonian is Hermitian on Hilbert space with measure a to the power 1 minus p minus 2q. This Wheeler-DeWitt equation can be solved by separation anthrops, and the stationary states for this model are written. Out of these stationary states, only positive energy states phi1 are orthogonal, and these states are used to construct the unitarily evolving wave packet for this model. The wave packet is constructed from these positive energy modes using a Poisson-like distribution, which gives us sharply peaked wave packet along classical trajectory. To make expression of wave packet simplified, we make distribution parameter a function of operator ordering parameter, which is kappa is equal to 1/3 mod of p plus 1. Since we make this particular choice, in the further analysis, we cannot establish whether the dependency on p is an artifact of operator ordering ambiguity, or it is coming due to its dependence on the shape of the distribution. So anyway, with this choice, the wave packet takes this simplified form given in equation number 9. The expectation value of energy with this distribution comes out to be inversely proportional to parameter lambda appearing in the distribution. The probability amplitude associated with the positive energy modes vanishes at classical singularity, thus avoiding singularity following DeWitt's criteria. And any wave packet constructed from such modes also avoids singularity. Now the expectation value of scale factor was computed in this wave packet, which is given in equation number 10. It is a well-behaved function which has global minima at tau is equal to 0. And for large tau, that means when tau is very, very large than lambda, it is proportional to tau to the power 2/3, thus following the classical trajectory. For simplicity, we will work with R-square measure and this representation of momentum operator, which is Hermitian with that measure. This particular choice made this constraint on the operator ordering parameters. It is not shown here, but we have proved that in the context of this model, the parameter Q doesn't have any observational imprint. That means for any general observable, the expectation value in general wave packet comes out to be independent of parameter Q. Thus, this constraint on parameter does not change the physical content of the theory. Now, the first thing that we can do is from the expression of scale factor in equation 10, we can find the Hubble parameter, Ricci scalar, and Krushman scalar. So these quote-unquote semi-classical expression for these parameters are given in equation number 11, 12, and 13. Here we can see that these functions are well behaved at the point of classical singularity at tau is equal to 0. And for the case when tau is very large, the classical expressions for these observables are recovered. We are interested in making these observables function of phase space variables and write Hermitian representation for them. For these Hermitian operators, then we would like to find the expectation value in the given wave packet. Now the Hubble parameter as function of phase space variable is given in equation number 14. The factor ordering for which since this Hubble parameter is also product of scale factor and its conjugate momentum, it also exhibit operator ordering ambiguity. The factor orderings for which the Hubble parameter is Hermitian is given in equation number 15 and 16, but but all these operator orderings, when acted upon a function, gives the same differential operator form. Thus, they are same on shell. The hermiticity of Hubble parameter hermiticity of Hubble parameter is there provided this boundary condition should be satisfied, which impose this constraint on the parameter of the wave packet. That means this Q should be non-zero in the wave packet. The expectation value of Hubble parameter for this wave packet is computed and is given in equation number 19. We recover the semi-classical expression obtained previously. Again, for large lambda, we recover classical expression, and this function has a global maxima at tau is equal to lambda by 2 and global minima at tau is equal to minus lambda by 2. Now, in the same way, we can write Ricci scalar as a function of phase space variable as well. Its canonical form is given in equation number 20. Ricci scalar also exhibit operator ordering ambiguity. General symmetric factor ordering of two classes are proposed for the Ricci scalar. First, trivial symmetric ordering in equation number 21 and while ordering in equation number 22. Here, parameters small j and small k encapsulate the operator ordering ambiguity in Ricci scalar. In both cases, the hermiticity of Ricci scalar implies that this boundary term should vanish, which put this constraint on the parameters of the wave packet. That means mod q should be greater than 3 by 2. Now, the expectation value of Ricci scalar in this wave packet is given in equation number 23 and 24 for both cases. We see that in the allowed parameter regime, these expressions are well behaved at tau is equal to 0. Also, the classical expression for both cases are recovered for large tau. Furthermore, we see since the dependence of j is j, so this j appear here only, and if we take q to be very large than j, then the signature of the operator ordering parameter will not be there in equation number 23, and similarly in equation number 24. So therefore, for q very greater than j and k, the Ricci scalar has local minima at tau is equal to 0 and global maxima at which asymptote to tau is equal to plus minus lambda by 2 when q goes to infinity. Now here I have plotted Hubble parameter as function of time. So at classical singularity, Hubble parameter vanishes instead of diverging. For large lambda, which means that dust cloud of lower energy, the amplitude of the maxima decreases. And for large tau, the classical behavior is recovered here. Next, I have plotted the Ricci scalar for different factor orderings. So on x-axis, I have tau, and on y-axis, I have r as function of tau. So these plots are for trivial symmetric ordering, and I have taken lambda is equal to 1 and small q in the first case. Here we can see that the signature of operator ordering is most pronounced at the point of classical singularity. And we see as we start increasing q, for small q, tau is equal to 0 is the point of global maxima. And when we start increasing q, tau is equal to 0 becomes the point of local minima with non-zero tau to global maxima there. And for very large q, we see that all three plots merge together, and we have no signature of operator ordering ambiguity parameter small j in this case. Here in this slide, I have plotted the Ricci scalar as function of operator ordering parameter at various stages of evolution. So these different color codings are for different tau values. In the first plot, we see for lambda is equal to 1 and small q, the tau is equal to 0 case is most sensitive to operator ordering parameter small j. There is small dependence for tau is equal to 1 case as well. But the later stages are insensitive to the operator ordering ambiguity parameter. As we increase q, even tau is equal to 1 becomes independent of j, while tau is equal to 0 case still has dependence on j, although it is very small. For q very large, even tau is equal to 0 has no dependence on operator ordering parameter as we have seen previously. Now this behavior seems interesting, but we cannot be sure whether it is coming from theory's dependence on operator loading parameter Q or whether it is due to dependence on the shape of the distribution. Next, we can ask what happens when we change lambda, which represents the energy of the dust. As we increase lambda, Ricci at later stages start depending on parameter J with scale over which the dependence is although small. For very large lambda, there is that is for small energy dust. Even tau is equal to 100 case is parameter J dependent is sensitive to parameter J. Although this dependence, as we see from the y-axis, is very small. So here we have plotted the Ricci scalar for while ordering as well. So here the first thing we notice is that for certain parameter set it attains the negative values, which is classically forbidden. Again, operator ordering ambiguity is most pronounced at classical singularity, and we see for large Q there is no signature of operator ordering ambiguity. Again, we have plotted Ricci scalar as function of parameter J at various stages of evolution, and the results in this slide are similar to what we have seen for the trivial ordering as well. So now we have also written the Krishna scalar as function of phase space variables as well. First, we write few trivial symmetric orderings. The hermiticity of the operator implies this boundary condition must be satisfied. Here, prime is derivative with respect to scale factor, and this boundary condition translates to this constraint on parameter Q. That means this Krishna scalar is Hermitian for only the wave packets where Q is greater than 9/2. The expectation value of Krishna scalar with the given wave packet is given in equation number 29 and 30. So these functions are also well behaved for the allowed parameter range at tau is equal to 0. Next, we consider while ordered Krishna scalar with these two operator orderings in equation number 31 and 32. The expectation value of Krishna scalar is given in these two equations. So here as well we can see that these expressions are well behaved at tau is equal to 0, and classical expression in this case is also recovered irrespective of the operator ordering when we have tau very large than the parameter lambda square. So here I have plotted the Krishna scalar as well. So we can see that for the while ordering K3 and K4 case, it here as well attain negative values for small q parameter, and the signature of operator ordering is most pronounced at the classical singularity here as well. And as we keeps on increasing q, we see that the signature of operator ordering vanishes for very large q. Okay, so on summarizing, so we have found that singularity avoidance in this quantum cosmology model is robust, and all the observables are well behaved. Far away from singularity, quantum effects washes away, and classical expressions are recovered. The signatures of parameters quantifying operator ordering ambiguity is maximum near the classical singularity. Thank you for your attention, and the floor is open for questions.
Yeah, thank you so much for your talk. So, so we can go for a one quick question, please.
I have a question.
Yes.
You are constraining tau with respect to lambda. You said that tau much greater than lambda for your results. But when you plot the graph and the tau is on the x-axis, then how we can compare if lambda is fixed there, then tau is greater than lambda? How we can describe it?
No, actually, what I am saying here is that in this regime, when tau is very large, the classical expression is recovered. So classically, we see that all these Hubble parameter Ricci scalar are inversely proportional to tau. So therefore, they must go to 0 in large tau limit. This is what we see in these plots as well. So for large tau, this behavior is somewhat related to 1 upon tau character, and this is 1 upon tau square character, and so on. So
And
what
when
I'm
okay, what do you comment about when tau is equal to 0? Because Hubble parameter is inversely proportional to tau. When tau is equal to 0, then
yes. Yes. So in this quantum model, so we have computed the expectation value of Hubble parameter, which is given in this equation number 19. So we can see
yes.
that tau is equal to 0 limit is not problematic anymore. So this at tau is equal to 0, Hubble parameter vanishes while Ricci scalar attains a non-zero value. So these functions are well behaved at tau is equal to 0, and for large tau, these functions, the classical expressions are recovered.
Okay. Okay. Thank you.
Yes. Okay. Thank you for the question.
Thank you so much for your time. And
Thank you.
let's
Thank
go
you.
to our next speaker, Amal Majid.
Yes, I'm available. Should I start my screen sharing?
Yeah, thank you so much.
Okay, so should I start?
Yeah, you can start. Thank you.
Okay, thank you. So I'm Amal Majid from University of the Punjab, and today I'll be presenting the topic decoupled quark stars in self-interacting branch-state gravity. And I'll start by explaining the important terms appearing in the title. So I'll start by quark stars, but before I move on to this topic, let's first take a quick look at what stellar structures are, how do they evolve, and how do they then end up as compact states. Sorry, I'm having some trouble moving my screen. Okay, it's moving. So can you see the slide?
Yeah, now we can see it.
Okay, thank you. Okay, so stars like things in the universe begin very small. They exist as mere particles in vast clouds of dust and gas, which are known as nebulae. Now, these clouds may remain cold and dormant for a long time until ruptured material from some galactic event enters these clouds at very high speeds. Due to this, the particles begin to collide and clumps are formed. And over a course of million years, these clumps grow into a young star, which is known as a protostar. So at this stage, the star is still in the process of gathering more dust and gas. And as it gathers dust and gas, its temperature increases as well. So if this star is able to attain a mass of around 0.08 solar masses, then it means that its temperature within the core has reached around 10 million Kelvin, and which is sufficient temperature for the hydrogen fusion reactions to begin within its core. However, if the star is unable to attain this mass, then it will end up as a brown dwarf. However, after a long time, even the protostar, sorry?
Yeah, nothing. You just.
Okay. So, however, after a long time, even the intake of the protostar exceeds its output, and two massive gas jets erupt, leaving behind a main sequence star. So this is the main phase of the life cycle of any star. It is in equilibrium, and how long a star stays in this phase depends upon its mass. Because for a highly massive star, it will have to burn through its fuel more quickly to support itself against the inward pull of gravity. So at the end of the main sequence phase, the star expands around 100 to 1,000 times the size of our sun today. So the energy is spread over a larger surface area, which causes the star to shine towards the red edge of the spectrum, hence giving it the name red giant. So what happens after that depends upon the mass of the parent star. It will either end as a white dwarf, which is a compact object, or it will blow up in a supernova. So supernova is an explosion in which the star collapses and then explodes. Initially, the outer layers of the star begin to collapse with the core, but then they rebound and are violently thrown outward, and a huge amount of energy is released. So once again, depending upon the mass of the core within the supernova, either a neutron star or a black hole is formed. So these three objects, that is white dwarf, neutron star, and black hole, are the well-known stellar remnants of gravitational collapse. However, another hypothetical object is a quark star. So what are quark stars? But let's first see what are quarks. So quark is the most fundamental known element to mankind. And as we can see from the simple diagram, that quarks basically make up all other particles. So these are the building blocks of other particles, and they can never exist in isolation. Even if one tries to spend some energy to separate them, the energy spent will in turn produce more quarks. Okay, so this is a diagram showing how the energy spent turns the original quark into more quarks. Okay, so there are 6 types of quarks known as up, down, strange, charm, top, and bottom. The up and down quarks have the lowest masses and they are generally stable. That is protons, and that is why protons and neutrons are made up of these quarks, whereas the remaining 4 types of quarks can only be produced in high energy collisions. So now coming back to what a quark star is. It is a hypothetical object since it has not been discovered as yet, but it is believed that for a slightly massive neutron star, the high temperature and extreme pressure within its core may cause the protons and neutrons to deconfine into a bath of quarks. And it is believed the density of these stars would be much higher as compared to a neutron star, whereas their masses would lie between 3 to 5 solar masses. So there is no certain equation of state to represent the structure of a quark star, and in the absence of best fit, the MIT Black model has been frequently used to construct these structures. This equation is presented in the equation presented in this slide. Here PR is the radial pressure, rho denotes the energy density, and B is the back constant. So the back constant basically differentiates between the true and false vacuum, and different values of this constant represent different scenarios. For massless strange quarks, the range of the back constant is 58.9 to 91.5, whereas for massive quarks, the back constant lies within the range 56 to 78 mega electron volt per femtocubic meter. In fact, the gravitational event 170817 suggested the detection of strontium. And it basically stated that neutron stars and quark stars are like fossils, if they are discovered, that is, which would allow us to peek back into the time, which is to the beginning of everything. Now, since I'll be constructing the solutions in the context of self-interacting branch decay theory, so I'll give a brief overview of as to why and how this theory was developed. So it was developed on the basis of the Dirac's large number hypothesis, where he compared the ratios of size scales and force scales in the universe and arrived at the equation presented over here, where G is the gravitational constant and M and R denote the mass and radius of the universe. However, when Hubble also discovered that the universe is expanding. In fact, farther a galaxy is, the faster it is receding from us. So the meanings of M and R would now mean basically that M is the mass of the visible universe and R is the radius of the observable universe. Now, why is that? Because it is possible that light from distant parts of the universe has not had sufficient time to reach us. So as with the passage of time, light does reach us, it means that M and R may vary with respect to cosmic time, which in turn implies that the gravitational constant would also vary. So based on this idea, in 1961, Brans and Dickey introduced a scalar tensor theory by representing the reciprocal of varying gravitational constant through a massless scalar field, which was coupled to gravity and matter through a coupling parameter. Now, this parameter can be tuned to get the desired results. However, the low values of coupling parameter have been used to describe the early inflationary era of the cosmos. But for weak field situations, the coupling parameter must be greater than 40,000 to attain the required results. So in order to resolve this conflict, a self-interacting potential was added to the action of branch decay theory, which led to self-interacting branch decay theory, whose action is presented on this slide. Here, G denotes the determinant of the metric tensor, zeta is the massive scalar field, R is the retreat scalar, and V denotes the self-interacting potential, whereas LM is the usual Matter-Lagrangian. So weighing this action with respect to the metric tensor and the scalar field, the field equations and wave equation are obtained, which are presented on the first and second equations on this slide respectively. Here, capital G gamma delta is the Einstein tensor, capital D gamma delta is the well-known energy momentum tensor, and box denotes the D'Alembert operator. So whenever a solution of the field equations is formulated, which represents stellar structures, it must satisfy certain conditions. So let's take a quick look at what these properties are. So the first one is redshift. So whenever light tries to climb out of a gravitational well, it expends some energy, and that is basically in the form of it extends its wavelength. So it shifts towards the red end of the spectrum, and hence the phenomenon is given the name gravitational redshift. So in order to calculate the redshift, the formula is presented in the first equation on this slide. And according to Ivanov, the redshift must be less than 5.211 for anisotropic fluids. Here, mu is the compactness parameter. Right.
Hello.
Yes. So first is the causality condition, which basically states that the speed of light, the speed of light, and which states potential and components of velocity must.
Amal, we can't hear you, and your screen has been disappeared.
I think we lost her.
I sent her a message.
Okay.
Yeah,
Also, sorry, I'm back.
Yeah. Okay. You just go ahead.
So, okay, continuing from where I left off. So the three criteria that I'll be using to check the stability are the causality condition, cracking approach, and adiabatic index, whose mathematical inequalities are presented here. Here, V perp and VR represent the tangential and radial velocities of sound. So basically, this condition states that the sound speed can never be more than the speed of light, and they have used relativistic units. So C has been taken equal to 1. The second criteria was built on Herrera's cracking approach along with causality condition, and its the bounds are presented in the second inequality on this slide. Whereas the third criteria measures the stiffness of the system, and for a stiff system, if the energy density is disturbed slightly, then the radial pressure increases sufficiently to balance itself against the internal perturbation. So the formula for calculating the adiabatic index is presented in the third equation. And according to Huntsman and Hilbrand, it must be greater than 4/3 for a stable structure. Okay, some other conditions that must be satisfied are that the meter coefficients of the solution must be positive and increasing. The parameters, that is density and components of pressure, must be maximum at the center and then decrease towards the boundary. The radial pressure must vanish at the boundary. The anisotropy, that is the difference of the components of pressure, must be 0. And the solution is viable if the 4 energy conditions are fulfilled, which are weak, null, strong, and dominant energy conditions. And the respective mathematical representations are presented over here. Okay, so I'll be calculating the solutions by applying the decoupling scheme. So what is this decoupling scheme? In this scheme, we take a well-known solution and then extend its domain by adding an additional source. So as we can see here, that T gamma delta represents the original source, whereas theta gamma delta is the additional source, which is coupled to the original source through the decoupling parameter sigma. So giving a step-by-step overview of how this scheme works. So we add a new gravitational source, and then we deform the metric potentials to decouple the field equations into 2 sets. So the first set corresponds to the original source, whereas the second set is related to the additional or the new source. Then the first set is solved by assuming a well-known solution. And for a second set, we usually use constraints and then solve it as well. Finally, we combine the solutions of both the sets to form a new solution of the extended domain. So decoupling can be applied either through minimal geometric deformation or extended geometric deformation. However, I'll be discussing only the first one, that is MGD. In this scheme, only the radial metric potential of the space-time is deformed, and it works as long as the interaction between matter sources is purely gravitational. So now I'll be applying decoupling in the context of self-interacting Browns-Sticky gravity. and use the MIT back model to construct structures that represent quark stars. So I'll start with a static sphere, which is represented by the first equation on this slide. And the matter distribution within this sphere is presented through the energy momentum tensor in the second equation on this slide. Here, basically T gamma delta M is the original source, and theta gamma delta is once again the additional source. So the field equations for this scenario are presented on this slide, while the modified terms are presented here. The wave equation is presented in the first equation, whereas the second equation shows our choice of the potential function for this work. And here m zeta basically represents the mass of the scalar field. Okay, so now according to the decoupling scheme, we must apply a transformation in the radial component. And here nu basically represents the deformation function. And lambda is the metric corresponding to the original, that is the isotropic source. So after applying the transformation, the field equations can be split into two sets. And the first set is obtained by substituting sigma equal to 0. And as we can see from these field equations that it exclusively incorporates the properties of the isotropic source only. Isotropic source, that is the original source. And for the second set, you can see which is a components of the additional source. So if we check the conservation of both sources, we can see them are which means that matter between, and the appearing in the second equation are presented here. Okay, so now the solution can be obtained. We have split the field equations into two sets. The first set will be specified by using an isotropic solution. So I'll be using two isotropic solutions. The first one is Tolman 5, which is presented in the first equation over here, and B, N, F, and W are constants. For the second solution, I'll be basically constructing it using Kramarker's condition, which is presented in this equation. And I'll assume a well-behaved radial metric potential of the form presented in the first equation on this slide. So using these two, I have constructed a temporal metric function as well, which is presented in the second equation. So this is the second isotropic solution that I'll be using to specify the first set. Here, A, B, C, Q1 and Q2, alpha 1 and alpha 2 are constants.
Amal, can you hear me?
So once the first set has been, yes, I can. Can you hear me?
I'm sorry, you need to be really quick because you have 4 more minutes. And then meeting link will be finished automatically.
Okay.
So please speak. Thank you.
Okay, okay. I'll just cover it. Okay. So the only 4 unknowns remain to be determined, and we have 3 equations. So that means I need 1 extra constraint, and I'll be using MIT back for that. So extending the first solution, I obviously obtain the values of constants through the matching conditions. These are presented here. Then I've applied the MIT back model, which yields this differential equation, which will be solved alongside the wave equation, obtain the deformation function. The graphical analysis has been done for these values of the parameters for 3 stellar structures as presented on the slide, and some important values are presented in this table. So quickly graphically analyzing the first anisotropic extension, we can see that the metric potentials are positive and increasing throughout the interior. The state parameters, density, radial, and tangential pressure are positive and then decrease towards the boundary. However, we can see that anisotropy is not 0 at the center as it should be, and it is positive only for 4U160852. Now, since the 3 state parameters are positive, it means that the first 3 energy conditions are satisfied for sigma equal to 0.2 and 0.9. And so therefore, I'll be checking only the dominant energy condition, and we can see that the solution is viable for both values of the decoupling parameter. Checking the compactness and redshift of the solution, we can see that these parameters lie below the required limits for both values of the decoupling parameter. Finally, checking the stability of the first anisotropic extension, we can see that it is stable for the considered values of the parameters. So quickly moving on to the second anisotropic extension. Once again, the unknown constants have been evaluated via the metric conditions. The MIT bag model, once again, it is applied to obtain a differential equation, which can be solved to obtain the deformation function. Same values of the parameters are used, and some important values are presented in this table. So quickly analyzing it as well. So the graphical representation over here shows that the metric potentials are positive and increasing. The state parameters are once again maximum by the center and then decrease towards the boundary. Moreover, anisotropy is 0 at the center and then increases for the 2 stars, whereas it is negative for her x1. The same behavior is obtained for sigma equal to 0.9. Once again, all the energy conditions are fulfilled, so this solution is viable. The compactness and redshift parameters for sigma equal to 0.2 and sigma equal to 0.9 lie below the required limits. And the solution is stable. However, for the star force view 160852, we can see that the adiabatics lies a little bit below the required limit, but increases quickly after a small distance for sigma equal to 0.2 as well as for sigma equal to 0.9. So let's just conclude the talk first. Okay, so we have basically formulated anisotropic solutions through MIT bag model in the context of self-interacting branch decay gravity by considering metric coefficients of 2 isotropic solutions. So the field equations were split into 2 sets, and the first set was specified, whereas the second set related to theta, it was solved by using the MIT bag model to construct anisotropic Quark Star models. The graphical analysis showed that energy density and pressure observed the required trends. So for the first anisotropic solution, we can see from this table that the solution was viable as well as stable for the considered values of the parameters. Whereas for the second anisotropic extension, the solution was viable and stable. However, the star 4U160852 disobeyed the adiabatic index for a little distance from the center.
Yeah, you just,
so we have seen that a decoupling technique can be used.
Yeah, you just summarized the talk, please. We
Sorry,
are just
so we have seen that the decoupling technique can be used to construct stable structures. Yes. Okay, so that concludes my talk. Thank you so much.
Thank you so much for managing the time. So I think there is not a time for a single quick question as well. So thank you so much, Amal, for the talk.
Oh. Thank you so much for giving me the opportunity.
Thank you. Thank you so much to all the speakers and participants. So Vantha, are you there? No, he's not there. So thank you so much, everyone, for the wonderful time and the talk. So we will meet you guys on Friday on another session. So thank you so much. Goodbye.
Thank you. Goodbye.
Thank you. Thank you.